Hello again. This is Math 2115 coming to you from the College DuPage, and this is the conclusion of the lecture entitled Encryption Applications. Please be attentive while you watch the remainder of this video. Cryptosystems are the general vocabulary and structure that we have, but so far we've defined two families of ciphers, a shift cipher and an affine cipher. Now we introduce, and we also talked about block ciphers too, but now we introduce the notion of cryptosystem, which is a general structure for defining new families of ciphers. So a cryptosystem is a five-tuple. We have P, which is the set of all plain text strings. C is a set of all cybertext strings where they're encrypted. Capital K is the key space. That's all possible keys. Script D is the set of the encryption functions, and D is a set of decryption functions. And we denote by E sub K the encryption functions in script E corresponding to key K, and D sub K is the decryption function in DK that decrypts the cybertext that was encrypted using E sub K. And that is D sub K of E sub K of P is equal to, these are basically inverses of each other, so you get P for all plain text P. Now let's illustrate this with an example. And so what this is asking you to do is describe the family of shift ciphers as a cryptosystem. You know what to do. Let's see how you do. Well, okay, to encrypt a string of English letters with a shift cipher, we first translate each letter to an integer between 0 and 25, that is to an element of z sub 26. We then shift each of these integers by a fixed integer modulo 26, and finally we translate back to letters. To apply the definition of cryptosystems to this shift cipher, we assume our messages are already integers. That is, the messages are elements of z26. So we assume the translation between letters and integers is outside of the cryptosystem. Consequently, both the set of plain text P and the set of encrypted strings are the strings of elements of Z26. The set of keys K is the set of all possible shifts, so K is equal to Z26. Those are the only shifts that you can do that will make sense in this. The set of script D consists of all the functions of the form E sub K of P equal P plus K mod 26, and the set of decryption functions is the same as the set of encryption functions, where D sub K of P is equal to P minus K modulo 26. Now, this concept is useful in the discussion of additional families and is used extensively in cryptography. Cryptography, I guess I should have said. Let's talk about public key cryptography. Now, all classical ciphers, including the shift and affine ciphers, are examples, and also the block ciphers that we're talking, are examples of private key cryptosystems. In a private key cryptosystem, once you know an encryption key, you can quickly find the decryption key. So if you know how to encrypt using a particular key, it allows you to decrypt the message easily, and we've talked about that already. You know how to crypt. So when a private key cryptosystem is used, two parties wishing to communicate in secret must share a secret key, because anybody that knows this key can both encrypt and decrypt. And two people who want to communicate securely must securely exchange this key, and that's another issue, and we'll talk about a way of doing this later in this lecture. So the shift cipher and the affine cipher are private key cryptosystems. They're quite simple and are extremely vulnerable to cryptanalysis the way we've shown. However, the same is not true of modern private key cryptosystems. In particular, the government has defense standard encryption keys and standards for private key encryption that are very advanced, and the advanced encryption standard is extremely complex and is highly resistant to cryptanalysis, although there's hacking that even happens with this, but it's very complicated, and it's beyond the scope of this course to discuss this in detail. AES is widely used in government and commercial communications, but it still shares the property that a secure communications key must be shared. And for extra security, a new key is used for each communication session because they don't want the key being stolen. So that requires a method for generating keys and securely sharing them. And again, more about this later. So to avoid the need for keys to be shared by every pair of parties who wish to communicate securely, cryptologists introduced the concept of public key cryptosystems. When such cryptosystems are used, knowing how to send an encrypted message does not help decrypt the message. This is kind of an amazing thing, and you've got to think about this a little bit. Some people didn't really know if this could be done, and it is done, and we'll talk a little bit about it. In such a system, everyone can have a publicly known encryption key, but only decryption keys are kept secret, and only the intended recipient of a message can decrypt it, because as far it is currently known, knowledge of the encryption key does not let someone recover the plain text message without an extraordinary amount of work, such as billions of years of computer time. And the example of this would be if you're buying something from Amazon, you want to be able to, your computer wants to be able to encrypt your credit card information and send it to Amazon, but only Amazon is able to decrypt it. So that's an example of public key encryption, because Amazon uses the same public key encryption for everyone. In 1976, some people at the Massachusetts Institute of Technology, Rivest, Shamir, and Adelman introduced a public key encryption, and this is known as RSA Systems, and they have their own company, and this is actually a big deal. This was actually known before because the British intelligence community used this several years earlier, but they made it public then. And there are great references about the history of this. But in an RSA crypto system, each individual has an encryption key that are two things. It is N and E, where N is the product of two large primes. So N is the product of two large primes, P and Q. And they're very large, say each with 200 digits each, and then you multiply them together. And an exponent E that is relatively prime to P minus 1 times Q minus 1. So you see, we're talking about really big numbers and relatively prime E. So this is the product of two primes and things like that. So to produce a usable key, two large primes must be found. Now that means you have to find two large primes and agree on what you're going to do it, but really it's just you have to pick the two large primes. This can be done very quickly on a computer using probabilistic primality tests. We have talked about that and referred to in earlier lectures. However, and the product of these primes with approximately 400 digits cannot, as far as currently known, be factored in a reasonable length of time. Multiplying is much faster than factoring. And as we will see, this is an important reason why decryption cannot, as far as currently known, be done quickly without a separate decryption key. Okay, so to encrypt messages using a particular key, N, E, we first translate a plain text message, M, into a sequence of integers. To do this, we first translate each plain text letter into a two-digit number. And we're doing what we did before, except if it only has a single digit, like perhaps B might be 0, 1. You use 0, 1, that makes it into two digits, okay? So B would be into 0, 1, and J would be into 0, 9. Then we concatenate these two-digit numbers into a string of digits. Next, we divide this string into equally sized blocks of 2 to the capital N digits, where 2 to the capital N is the largest even number, such that the number 25, 25, ... down to 25 with 2 to the capital N digits does not exceed lowercase n. When necessary, we pad the plaintext with dummy XXX's to make the last block the same size as all the other blocks. After these steps, we have translated the plaintext message into a sequence of integers M1 through Mk for some integer k. Encryption proceeds by transforming each block M sub I to a cybertext C sub I, and this is done using the function capital C is equal to M raised to the E mod n. Now, this is very big numbers, and you're using exponentiation mod n, like we talked about. To perform the encryption, you use an algorithm for fast modular exponentiation, and we talked about some of those earlier in our course. So we leave the encrypted message as blocks of numbers and send these to the intended recipient. Because the RSA crypto system encrypts blocks of characters into blocks of characters, it is a block cipher. So you're sending this is the cipher blocks. Okay, now we're going to look at an example illustrating how the RSA encryption is performed. For practical reasons, we're going to use small primes P and Q in this example rather than primes with 200 or more digits, and you can realize how involved that could get. Although the cipher described in this example is not secure, it does illustrate the techniques used. So what we're going to do is we're going to encrypt the message stop using RSA encryption with the key 2537, 13. And note that 2537 is equal to, it's the product of two primes. It is 43 times 59. So P is 43 and Q is 59. And we need to have an E such that the GCD of E, and that is P minus 1 and Q minus 1, is the greatest common denominator then of 13 and 42 times 58. Now, and we're forcing this to this greatest common denominator to be 1, so we can pick E to be 13. Okay, so to encrypt, we first translate stop into their numerical equivalents. Okay, because 2525 is less than this number, is less than that, we obtain this, and this is our blocks. We encrypt each block using the mapping. Cybertext is each block raised to the 13th power mod 2537. Now you should verify these computations. I should have put a little box here, but I didn't think of it. So computations using fast modular multiplication shows that 819 to the 13th power mod 2537 is 2081, and 1413 to the 13th, 1415 to the 13th power mod 2537 is 2182. Again, you should verify these calculations. So the encrypted message, once you encrypt it, is this and this. Okay, now the plain text, now that was the encryption. Now the plain text message can be quickly recovered from the cybertext when the decryption key D, which is an inverse of E modulo this, is known. Now such an inverse exists because they're relatively prime to P minus 1 and Q minus 1. To see this, note that if D times E is congruent to 1 mod P minus 1 Q minus 1, there's an integer K such that K times P minus 1 Q minus 1 multiplied by that is equal to 1, so it follows that C raised to the D power is M raised to the E raised to the D power is M to the DE. But that is going to be this mod N. I just do a substitution. So, by Fermat's little theorem, we know that M to the P minus 1 times K Q minus 1 is the same thing as 1. and that is m mod p. So you see when I have d, I just apply that exponent and it gives me this. And c to the d then gives me c to the d then is congruent to m times, and this is q minus 1 kp minus 1, and that is m mod q. Now because the GCD of p and q equals 1, it follows by the Chinese remainder theorem that c to the d is congruent to m mod pq. Pretty involved stuff, and especially with big numbers. So let's see what happens here then in an example, and I would encourage you to give this example a go. So you received the encrypted message, this and this, 2 blocks of 4. What is the decrypted message if it was encrypted using the same cipher that we had up here? Okay, the message was encrypted using Cryptosystem with n equal 43 times 59 and exponent 13. Okay, so D, the inverse of 13 mod 243 is 937. So we use 937 as our decryption exponent. And so to decrypt a block C, we take the block C and we raise it to the 937 mod 2537. So to decrypt the message, we use fast modular exponential algorithm to compute this raised to the 937 mod 2537 is 0704, and this one raised to the 937 mod 2537 is equal to 1115. Consequently, the numerical version of the original message is this, and translating this back to English, we see that the message is help. Check these calculations, please. Now, why is the RSA cryptosystem suitable for public key cryptography? Well, first of all, to rapidly find a public key by finding 2 large primes, each with more than 200 digits, and to find the integer e relative prime to that. That's what it is possible to do that. When we know the factorization of n, then we know p and q, and we could quickly find the inverse d. And this is done by the Euclidean algorithm to find the Boisot coefficients s and t for d and p minus 1, q minus 1. And this shows that the inverse of d modulo p minus 1, q minus 1 is s modulo p minus 1, q minus 1. So knowing d lets us decrypt messages sent using our key. However, no method is known to decrypt messages that is not based on finding a factorization of n, or that does not also lead to a factorization of n. Now, factorization is believed to be a very difficult problem as opposed to finding large primes in Q, which can be done quickly. The most efficient factorization methods known as of 2010 require billions of years to factor 400-digit integers. Consequently, when these are 200-digit primes, it's believed that message encrypted as a modulus cannot be found in a reasonable time unless P and Q are also known. That means this is considered bulletproof. But there's a lot of progress that are made. So although no polynomial time algorithm is known for factoring large integers, this is a subject of active research to find new ways. And integers that were thought once upon a time as being too large to be factored can now be factored. Integers with more than 150 digits, as well as some with more than 200 digits, have been factored using team efforts. When new factorization techniques are found, it'll be necessary to use larger and larger primes. Now, fortunately, there are an infinite number of primes, but unfortunately, that means we have to be very vigilant about the research to make sure we're using big enough primes. This is widely used, and both public key systems for Amazon-like applications and private key applications for government communications. For example, a public key crypto system such as RSA can be used to distribute private keys to pairs of individuals when they wish to communicate. These people can then use a private key for encryption and decryption of the messages. So see, you're using both public key and private key encryptions and using the RSA algorithm to share the key, the private key. So far we have shown how cryptography can be used to make messages secure. However, there are many other important applications of this, which are exchanges of message carried out to achieve a particular goal. For example, we're going to show how this can be used to allow people to exchange a secret key over an insecure communications channel, and then they can communicate with the private key and also update the keys. We will also show how cryptography can be used to send signed secret message so the recipient can be sure that the message came from the purported sender. And this stuff gets really deep, but we will look at simple examples. Here we'll talk about key exchange, okay? And this is called the Diffie-Hellman Key Agreement Protocol. And let's talk about a simple example. Again, this was used by the British Secret Service long ago, but not until 1997 was this made public. So here we'll talk a little bit about this. So suppose we have an Alice and Bob want to share a common key. So this is what they do, and the computations are done in ZP. So Bob and Alice agree to use a prime P and a primitive root A of P. Now that primitive root was something we discussed earlier, and you may want to refer back to that. Alice chooses a secret integer K1 and sends A to the K1 modulo P to Bob. Bob chooses a different secret integer K2 and sends A raised to the K2 mod P to Alice. Alice computes this and Bob computes this. Now you see they're both computing the same thing because of properties of integers, but K1 and K2 are secret because they've already done their encoding. At the end of this protocol, they have computed their shared key, namely this one. To analyze the security of this protocol, note that the messages are step in 1, 2, and 3 are not assumed to be sent securely. We can even assume that these communications were in the clear and the contracts are public information. So people know this and they know this, but the protocol ensures that K1 and K2 and the common key A are secret. So to find the secret information, that requires that an adversary, someone trying to break the code, must solve instances of the discrete logarithm problem, which is very hard. And I think I really said that. This is thought to be computationally infeasible when the numbers P and A are large. But again, ongoing vigilance has to be found. Another application is sending digital signals. Not only can cryptography be used to secure the confidentiality of a message, but it can be used so that the recipient of a message knows it came from the person they think it came from. We first show how a message can be sent so that the recipient of the message will be sure the message came from the purported sender. In particular, we can show that this can be accomplished using RSA cryptosystem to apply a digital signal to a message. So suppose the Alice that we were talking about before's RSA public key is NE, and her private key is D. Alice encrypts a plain text message X using the encryption function E, and it depends on N and E, and that is X raised to the E mod N. She decrypts a cybertext message Y using the decryption function D, again, and this is X to the D mod N. Alice wants to send the message M so that anyone who receives the message knows it came from her. Just as in RSA encryption, she translates the letters into their numerical equivalent and splits the resulting string into blocks so that each block has the same size. And then she applies her decryption function to each block, obtaining this. She sends this result. When the recipient receives her message, they apply her encryption function to each block. that everyone has available because her key is public information. The result is the original plaintext block because these two things are inverses of each other. So Alice can send her message to as many people as she wants, and by signing it this way, everyone is sure it came from Alice. And this is a explained a little bit more in the example. So suppose Alice's public encryption key is the same as in the earlier example. N is 43 times 59 equal 2537, and E is 13. Her decryption key, we remember, was 937 as described. So she wants to send the message "meet me at noon" to her friends, and she wants them to sure it sends to her. What should she send? Well, she first translates into blocks of digits, getting this, and then she applies her decryption transformation to this, to each block. And using fast modular explanation, she finds that this raised to the 937 mod 2537 is this number to the 937 mod 2537, which is 555, and 19 raised to the 937 is mod 2537, and that is this number. And the third one, this is equal to this, and this is equal to this. That's the whole message. So the message she sends split in the blocks is this. But when each one of these friends gets the message, they apply her encryption transformation to each block. When they do this, they obtain blocks of digits of the original message, which they translate back to English letters. So we have shown that signed messages can be sent using RSA cryptosystem. And we can extend this by sending signed secret messages. So to do this, the sender applies RSA encryption using the publicly known encryption key of the intended recipient to each block that was encrypted using the sender's decryption transformation. The recipient then first applies his private decryption transformation, and then the sender's public encryption transformation. Pretty complicated stuff, and big numbers are hard to do without computers. In closing, and this is kind of one of my final comments, but most sciences, and including computer science, is mostly math. And if you can do the math, you can do anything. You can't study too much math. But in closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.